Good morning. In the previous class we studied about the theoretical aspects of the sedimentation tanks, and we have to now discuss about the types of sedimentation tanks. Sedimentation tanks may be classified into the fill and draw type and then continuous flow type. Fill and draw type or the continuous flow type. So in this fill and draw type of sedimentation tanks, the water is filled to the tank by closing the outlet valve that is provided at the bottom. So in the fill and draw type, there will be only two valves. One is the inlet valve and another one is the outlet valve. The outlet valve, which is kept slightly above the sludge zone, that is few centimeters or meter above the floor level of the tank, and while water is being filled, that outlet valve is being kept closed, and when once the tank is filled with the water, then the inlet valve is also closed. Then the water is made to stand for some predetermined time, that is called the detention time. So during this period, when the water is kept still without any movement, then it's going to lose its sediments, that is the suspended and settlable particles, to settle down because of the properties of these particles, like its size, its shape, and also the density, specific gravity, viscosity of the water, etc. These particles are pulled to the floor or bottom of the sedimentation tank. Hence the water is a large proportion of the suspended particles got removed by settling down to the floor, and after this end of this designated detention period, then the outlet valve is opened so that we can withdraw the settled water, which is comparatively clearer because a major portion of these particles have been now removed from the raw or incoming water. So this is called the fill and then draw type. So in practice there will be a series or several number of tanks will be there in parallel. So when one tank is filled, then it is the flow to that tank is closed and then it is diverted into the next. Like this the process continues. So this is called the fill and draw type of sedimentation tank. And based on this flow, the second type of tank is the continuous flow type of sedimentation tank. In this continuous flow type of sedimentation tank, the water is continuously kept moving in the sedimentation tank. That is, the water enters the tank through the inlet valve, and at the same time the settled water is also being withdrawn from out of these tanks continuously. That is, simultaneously both there will be entry of the raw water into the tank, and at the same time there will be withdrawal of the settled water out of the tank. So such tanks are called as the continuous flow type of sedimentation tanks. Then depending upon the shape of the sedimentation tanks, see, the shape of the sedimentation tanks may be either they may be square or rectangle or even circular tanks. Sometimes even they may be oval or any other shapes. In general, most commonly, these rectangular, square or circular tanks are commonly being used. Now, we shall try to design these sedimentation tanks. Design in the sense we have to arrive at the dimensions of the sedimentation tanks. We already discussed about how an ideal sedimentation tank is divided. So an ideal sedimentation tank is divided into 4 zones. The entry of water into the tank, so a few centimeters or hardly 1 or 1.5 meter from the inlet zone, up to that it is called as inlet zone from the entry of the water to the tank. And then at the farther end there will be about an equal amount of the space is provided for withdrawal of the water without creating any turbulence. That is called the outlet zone. And at the same time, at the bottom of the tank we will have to provide sufficient space for sludge accumulation. Therefore that zone it is called as the sludge zone. So the space between this inlet zone, outlet zone and also above this sludge zone, that zone it is called as the settling zone. So we have some of the important parameters or the terms that are used as the design parameters. So among them it includes the very important design criteria is the detention time. So this is an important term used in the design of the sedimentation basin. So it is the average theoretical time for which the water is detained in the tank. Hence it is the ratio of the volume of the basin to the rate of flow or the discharge through the basin. We know that the volume or capacity of the tank is nothing but it is the product of the flow or the discharge multiplied by the time. Therefore, if we want the time, we will have to divide that volume or capacity of the tank by the discharge, so that the ratio of C by Q, C to Q, C by Q is nothing but the detention time. Say for the rectangular tank, the volume or the capacity of the rectangular tank is given by length, breadth and the height. Therefore it is L into B into H that constitutes, that will give you the volume, and in the denominator the flow, that is expressed in terms of the letter Q. Therefore for rectangular tanks the detention time is LBH divided by Q. However, for the circular tanks this detention time TC, it is given by within the bracket 0.011 small d plus 0.785 capital H into d square divided by Q, where d is the diameter of the tank, H is the vertical depth at the wall or side water depth. The detention time usually ranges from 4 to 8 hours for plain sedimentation and 2 to 4 hours for sedimentation with coagulation. Now we shall know about the usual dimensions of some of the common rectangular tanks. The width of the rectangular tank may be about 10 to 12 meter and its length is normally 4 times its width through, though sometimes it varies from 1 to 6 times. Therefore the length of the tank may be from 1 to 6 times its breadth. If it is 1 to 1, then it is a square tank, or the rectangular tanks may have its length equal to 1 to 6 times the width. The cross-sectional area is such that the horizontal flow velocity, that is horizontal flow velocity, should be maintained in the range of 0.15 meters to 0.30 meter per minute, that is 15 centimeters to 30 centimeters in 1 minute. That should be the horizontal flow velocity of the water in a continuous flow type of sedimentation tank. The area and the depth of the basin determine its capacity. The area and then the depth. Area here it is the surface area multiplied by the depth of a basin determine its capacity and hence the detention time. The depth, however, is much less important than the surface area. Though the lengths of 30 meter are common, even there are some examples whose lengths are around 100 meters or more. They also have been adopted. The diameter of the circular tanks may be up to 60 meter are in use, but however if the diameter of the circular tanks is ranging from 10 to 20 meters, so then it will be ideal or good or easy for maintenance of the sludge cleaning equipment and properly monitoring the sedimentation tanks. Square tanks are also there sometimes, but usually their sides will be up to a maximum of 20 meter. Next, we shall understand these design concepts and how to arrive at the dimensions of the sedimentation tank. Before that, we shall also work out one problem to determine the settling velocity of the particle in the water. So the first example goes like this. To find the settling velocity in water at 20 degrees centigrade of spherical particle of 5 into 10 power minus 5 centimeter, 5 into 10 power minus 3 centimeter diameter, having its specific gravity 0.8, given the kinetic viscosity of the water at 20 degrees centigrade is 1.01 into 10 power minus 2 centimeter square per second. So here the question is, does the particle settle or rise? And what would happen if the specific gravity of the particle in the second trial or situation is 1.2. So as per the Stokes law, the settling velocity is given by that equation, that is gd square into rho s minus rho within the bracket divided by 18 times mu, where mu is the absolute viscosity, and it is also given by density multiplied by the kinetic viscosity. So kinetic viscosity is 1.01 into 10 power minus 2 at 20 degrees centigrade, and density is 0.998. Therefore, the diameter is given, that is 5 into 10 power minus 3 centimeter. Rho s, that is the density of the particle, is 0.8. So therefore, mu is given by, that is density into kinetic viscosity. Therefore, 1.01 into 10 power minus 2 multiplied by 0.998 square centimeters per second. Here rho s minus rho w. So here rho s is, it is the density of the solid particles 0.8, and rho w is, it is the density of the water, which is taken as 1 gram per cc. Therefore, within the bracket, that is the term rho s minus rho w, that is density of the solids minus density of the water. Density of the solids is given as 0.8 and for the water it is 1. Therefore, we are going to get minus, that is negative 0.2. Therefore, the particle instead of settling down, the particle will rise to the top because of this negative sign. So in the second case, when the specific gravity of the particle is 1.2, then the settling velocity will become 0.027 centimeter per second, because within the bracket rho s minus rho w, where rho s is density of the solids, that is 1.2, and then this rho w is 1, therefore we are going to get 0.2 within the bracket, and after simplifying all the substituted values, we are going to get 0.027 centimeters per second, which is positive. So that the settling velocity is positive, means the particle is moving towards the floor of the tank with a vertical settling velocity of 0.027 centimeters per second, that is 0.27 millimeter per second. So this is the first example on this settling velocity calculation. Second example goes like this. We are asked to design a set of settling tanks of continuous types for the city waterworks having the population of 2 lakhs and supplying the water at the rate of 200 liters per head per day. The detention time may be taken as 2 hours, and if the alum is used at 1.5 milligrams per liter, you have to also calculate the requirement of the alum per month, and also you have to sketch the design of the settling tanks. So here given the data, population is 2 lakhs, the rate of water supply is 200 liters per head per day, detention time is 2 hours, alum dosage is 1.5 milligrams per liter. Therefore, the total quantity of the water required per day will be the product of the population and then the rate of water supply. Therefore, population is 2 lakhs and the rate of water supply is 200 liters per individual in a day. Therefore, the product of which it will become, say, 40 million liters, that is 4 into 10 power 7 so many liters, or it is 4 into 10 to the power of 4 cubic meters per day, that is 40,000 cubic meters per day will be the quantity of the water treated per day. And because the detention time is expressed normally in terms of the hours, we have to calculate the flow per hour. Therefore, hourly treatment of the water will become now 40,000 cubic meters divided by 24 hours. If you simplify that, we are going to get 1666.67 cubic meter. That is the hourly quantity of the water to be treated. And in the problem it is given as designing a set of settling tanks. Set means it should be more than one. It may be 2, 3 or any number. Unless it is given, you are free to assume. If it is given, you will have to take the number of tanks according to the data given. So now, providing 2 such settling tanks, say rectangular in plan, we are assuming it if the shape is also not given. So then the flow to each of these 2 tanks, it will become, that is hourly flow is 1666.67 cubic meter. But because we are providing 2 rectangular tanks in working at any time, therefore flow to each of the tanks will now become 833.33 cubic meters per hour. And given detention time is 2 hours and alum dosage is 1.5 milligrams per liter. So, therefore the capacity of the each tank will be, as I said earlier, C is equal to Q into T. That is, capacity of each tank is equal to the product of the flow and then the detention time. Here flow is 833.33 cubic meters per hour and the detention period is 2 hours. Therefore, the volume or the capacity of the tank is 1666.67 cubic meter. Assuming a horizontal flow velocity of water as 0.3 meter per minute. Therefore, the length of the tank required will be the distance travelled, and the distance travelled is equal to what? It is the velocity multiplied by the time. That is, length of the tank required will be the product of the velocity of the moving water in the tank multiplied by the time for how long it is kept in movement. Therefore, when the detention time is 2 hours, therefore it is 2 into 60 minutes, it is 120 minutes, and the velocity or the speed is 0.3 meter per minute given. Therefore, speed is expressed in terms of so many meters per minute, and then the time is also should be expressed in terms of minute, so that the length of the tank we are going to get 36 meter, because 0.3 meter multiplied by 120 minute, it's going to be 36 meter. Therefore, once we get the length of the tank, thereby the cross sectional area of this rectangular tank can be determined by determining the volume or dividing the volume of the tank by the length. We are going to get the cross sectional area of the tank. That is, capacity we got as 1066.67 cubic meters, and then the length we calculated as 36 meter. Therefore, if we divide this capacity by the length, we are going to get 46.3 square meter as the cross sectional area of the tank. And by providing the liquid depth as 3 meter, we will have to assume the depth of the water, say from minimum 2 meter, and it may go maximum 3.5 or up to 4 meter. That is the usual range of the water depth in the sedimentation tank. So in this problem, assuming the liquid depth as 3 meter, therefore the breadth of the tank required is what? So the cross sectional area constitutes what? It is the breadth of the tank and then the depth of the tank. So when the depth of the tank is assumed, we can obtain the width of the tank by dividing the cross sectional area by the depth of the tank, that is 46.30 by divided by 3 meter. Therefore 15.43 meter will be the width of the sedimentation tank. So we have arrived now the dimensions of the tank. That is, the length of the tank we have obtained as 36 meter, and then the breadth of the tank we got it as say 15.43 meter, and the depth of the liquid as say 3 meters. So once we have arrived at these dimensions, now we will have to check our design. The first check is the check for the overflow rate. So this overflow rate is nothing but it is the quantity of the water that is treated in a unit time, say per hour. So here in this case, each tank it's going to treat the water in 1 hour 833.33 cubic meter, and when this quantity is divided by the surface area, so then we are going to get the surface overflow rate. So this surface area is nothing but the length and then the breadth. So length of the tank is 36 meter and the breadth of the tank is 15.43 meter. Therefore, it's going to be 1.5 cubic meter per square meter per hour. 1.5 cubic meters means 1500 liters per square meter per hour. So usually the range is 1000 to 1250 liters per square meter per hour. So therefore, by providing the width as say 20 meter, because here the range suggested is only 1250 liters per square meter in 1 hour. Therefore, the obtained value is more than that, that is 1500 liters. Therefore, we will have to increase the surface area. So by increasing the width of the tank from 15.43 meters to some value, say 20 meters, we are providing as the width of the tank. Therefore, the overflow rate, now it will become this flow, that is 833.33 cubic meters divided by the plan area, that is 20 meter width and then the 36 meters length. Therefore, now it will be coming as 1.157 cubic meter per hour or 1157 liters per square meter per hour. So therefore, it is in the range, within the range of 1000 to 1250 liters per square meter per hour. Therefore, providing a free board of 0.5 meter, that is the free space above the water level, as well as providing a bed slope of say 1 in 36 for the sludge accumulation, the overall depth at the inlet of the tank, inlet end of the tank is 3 meter liquid depth plus 0.5 meter free board and 1 meter, that is the extra depth, because the floor or the bed of the tank is provided at 1:36, means for every 36 meter length 1 meter is the fall. Therefore, overall depth will be 4.5 meter and the depth at the outlet end, it is equal to the liquid depth plus the free board only. Therefore, 3 plus 0.5, 3.5 meter. Hence, provide two rectangular sedimentation tanks of 36 meter length and 20 meters, and at the inlet end the depth, liquid depth is 3.5 meter and overall depth it will be 3.5 meter at the outlet end. So at the inlet end it will be 4.5, at the outlet end it is 3.5 meters. The figure below will show you the cross section of the longitudinal section of the tank. So next thing is we will have to calculate what is the requirement of this alum per month, for which the dosage is given as 1.5 milligram per ml per liter, that is for every 1 liter we need to add 1.5 milligram of the alum to the water as the coagulant. Therefore, total quantity of water treated per day is 4 into 10 power 7 liters. Therefore, the quantity of the alum required each day, it will be 4 into 10 power 7 into 1.5 mg, or 4 into 1.5, it is going to be 6. Therefore, 6 into 10 power 7 milligrams, or it is 6 into 10 power 7 divided by 10 to the power of 6 in terms of kgs. Therefore, it will become say 60 kgs of the alum per day, and as monthly requirement is asked, we will have to multiply this quantity by 30 days. Therefore, 60 into 30, it is going to be 1800 kg or 1.8 tons.